Hey everyone, welcome to Math 104, section 1.6, set operations and compound inequalities. In this section, we're going to learn some very abstract material. It's going to be very important to develop a strong intuition for these ideas. And a great way to do that is by relating it to everyday real-world objects. So I'd like everybody to read the introduction and answer that first question about creating matching pairs of socks. Pause the video and read that through because I'm not going to stop. Alright, so Rhonda, in her basket, has a bunch of socks, red, brown, green, and so on. These are all the socks she has in her basket. And here's the socks that she has in her drawer. So we want to find the matching pairs. So anything that is in both sets, we can create a matching pair. So we have black and black, there's a matching pair. And we've got green and green, another matching pair. And blue and blue. Everything else, there's just one. White is in this set, but it's not in the drawer. Tan is in the drawer, but it's not in the basket. So those are the three matching sets of socks. Well, guess what? You just found the intersection between two sets. The first set is all the socks in her basket. The second set is all the socks in the drawer. And the intersection is what we get when we take those two sets and combine them in specific ways. With the intersection, we only want the elements that are in both sets. Anything that's in only one set is not included in the intersection. Another way to think about intersections is the intersections of two roads. So there's First Street, and then come the other way, here's Second Avenue. So the intersection is just a piece of concrete, blacked out, whatever you want to call it, right in the middle there. So over here, we're only on Second Avenue. So that would not be in the intersection. Over here, we're only on First Street. It's only right in the middle here where we're both on First Street and Second Avenue at the same time. So there's the intersection of two streets and the intersection of sets B and D, and the symbol for intersection is an upside down U. So we're taking set B and set D and combining them together into one set. And that set is black, blue, and green. All right, so in a more formal definition here, A intersect B is all numbers x such that x is in set A and x is in set B. So the number has to be in both sets in order to be in the intersection. So take that idea and apply it to your turn number one. So for part A, you got 2, 4, 6, 8, 10 for set A and 1, 2, 3, 4, 5 for set B. So the numbers that are in both sets are 2 and 4. All the other numbers are only in one of the sets, so that would not be in the intersection. The intersection is only the numbers that are in both sets. Now for part B, you've got even numbers in the first one and odd numbers in the second one. So there are no elements that are in both sets. So the intersection of A and B, remember that symbol we learned last time for a set with no elements in it? Empty set. So A intersect B is the empty set. All right, please read through the Gogebic Ski Emporium information there and answer the question, how many different types of ski brands will we have, and then write out the brands. Alright, so a customer calls, wants to know how many brands of skis they have. So at one location in Houghton, they got Rosenthal, Head, K2 Atomic, and Solomon. In Ironwood, they have Nordica, Solomon, Armada, and Rosenthal. So if the customer calls and wants to know how many brands they have, they're not just going to read off the brands from one store, they're going to read off all the brands from either store. So we have 7 different brands, and those brands are Nordica, Solomon, Armada, Rosenthal, Head, K2, and Atomic. So that means any brand that is in either location is included in the set. And that's the idea of the union between two sets. Any number that's in either of the sets is in the union. So it only has to appear in one of the sets in order to be in the union. Contrast that with intersection, where we need it to be in both sets. So that's the difference between the two. So the formal definition is just like intersection, except we have an or instead of and. Or meaning it can be in either set, and it's going to be in the union. With intersection, since there's and, it has to be in both sets. Okay, take a look at your turn number 2. We want to find the union of sets A and B. So for part A, we've got 3, 4, 5, 6, and 2, 3, 4, 5. So 2 is in one of the sets, so that's included. 3, 4, 5 are in both of them, so those are included. And 6 is just in set A, so that's also included in the union. So the union is 2, 3, 4, 5, 6. And the symbol for union is a regular U, like a capital U. So that's a great way to remember which symbol is which. Is the union looks like a U, and intersection, you just flip it over. Part B. Here we've got the evens and odds again. So you can write out all those numbers, or you can use an ellipsis. So establish a pattern with 3 numbers, 1, 2, 3. Ellipsis meaning it continues on in that pattern. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all numbers between 1 and 10 would be in the union. So in these examples, we've been looking at finite sets, but there are also infinite sets. So we're going to look at the unions and intersections of infinite sets. Now there's a table just below that summarizes all this information. And a table like this is a really effective study tool, because once you have the ideas down, you can just refer to the table to refresh your memory. So the keyword and corresponds with intersection. That's the upside down U. And when we graph it, as we'll see, we're going to graph the overlap between the two graphs. With or, that's the union, that's the regular U, and when we graph that, we're going to graph everything, anything that's in either of the first two graphs. So let's take a look at an example of this. There are several different cases as to how these graphs can come together. All right. First way is if both graphs point in the same direction. And it could be left or right, it doesn't matter. It's basically the same case. So there's one situation that can happen when we're combining two graphs. The other situation is we have one pointing this way and one pointing this way, and with no overlap in between them. And the last situation is if we're pointing in opposite directions, but there's some overlap. The two graphs cover the same area in the number line. So those are the 3 situations we're going to look at, and we're going to look at them for both intersections and unions. So that means there's 6 scenarios you have to be able to handle. They're all very similar and they all require the same skills, just a little bit different in each type. So case 1. we're going to look at the compound inequality, and the compound inequality is two or more inequalities. And in this course, we're only going to be covering two at a time, but it could be more, that are connected with either and or or. All right, so here's a compound inequality. Two individual inequalities connected with and or. And as we saw, and means intersection. So we're going to find the intersection of these two sets. So let's graph them individually. If we look at the steps for solving a compound inequality, is to solve each inequality individually. Well, they're already solved, so we can skip that step. Step 2, graph each solution set individually. So we're going to create two different graphs here. And you don't have to fill in all the numbers. Just put in the critical number here. And it can be helpful to line them up. I just put a 0 there to line them up. All right, so there's going to be our two individual graphs. X is greater than -1, so we'll put a -1 here. And we're looking greater than. It's strictly greater than, so that is a parenthesis. And going all the way to the right. Fill in the arrow to indicate it's infinite. There's our first graph. Now we've got x less than 4. So over here, right about here, it'll be a 4. Again, it's strictly less than, so that's a parenthesis. And we're going all the way to the left and fill in the arrow. Right, so there's our two individual graphs. Now we're going to combine these together. Right, we're combining them with and that means intersection. Intersection means it has to be in both of them. So over here, let's say we're going to see it. Let's see if 5 is going to be in our solution set. Okay. Well, 5 is greater than -1, so it's in this set here. But 5 is not less than 4. So if I start at 5 and I come down, I'm only hitting one graph. The other graph I miss. So that one is not in the intersection. All right, how about a -2? So -2 is less than 4, so it's in this graph. That's great. It's in that set. But -2 is not less than, or not greater than -1. So this one, we miss this graph, and we hit this graph. So we only hit one, so we're not in the set, right? Can't create a matching pair of socks. If this is confusing, keep thinking back to those examples, those real-world examples, creating a matching pair of socks. All right, we go with one pair of socks from this one pair of socks from this, or one sock from this one sock from this one. We want to create a pair. Only place we can create a pair is right here where we hit both graphs. Let's say the number 1. The number 1 is in this set because it's greater than -1, and 1 is in this set because it's less than 4. All right, there's our matching pair of socks right there. So that means the graph will only be the overlap. So I'm going to start here at -1, go out to 4, parentheses, just like we had in the original graphs, and then only shade the overlap. And there's the graph of x greater than -1 and x less than 4. Now writing that in interval notation then. -1 to 4 with parentheses. Your turn, number 3. Solve the compound inequality and graph the solution set. Well, it's already solved for you, so all you have to do is graph. And then write the solution set in interval form. So we're going to graph these two individually. X is less than or equal to 2. So there's 2. We have less than or equal to, so that's the bracket. We're going all the way to the left. X is greater than or equal to negative 5. So greater than or equal to gives us another bracket here. We're going all the way to the right. All right, now the period or the place where it overlaps is here between negative 5 and 2. So use a bracket just like we did above in both spots. Shade in between them. And then interval form of the solution set, negative 5 to 2. Just keep in mind you want to use the same symbols in interval form as you do on the graph. So brackets and brackets. All right, case 2, now we're going to look at graphs that point in the same direction. All right, now we've got x greater than 0 and x greater than 3. So if we graph those, again, these graphs, they don't need to be anything special. Just get the critical numbers in there. Okay, greater than 0, going to the right. Greater than 3, another parenthesis, going to the right. Strictly greater than, so it's parenthesis. All right, now we want the intersection. The intersection is the overlap. So here, we have no graphs. So definitely not here. Here, we just have one graph, missing this one. Here, we have both graphs. So when you hit both graphs, that's where you shade. It starts at 3, goes this way. All right, so like the first example, we were graphing the center part, the overlap. So we had endpoints on either side. But here, we're going all the way to the right. So you're going to have to use one of those infinite intervals. So 3 to infinity on the right. And there's our solution set in interval form and graph form. Your turn, number 4. We got x less than 7 and x less than negative 6. These are not necessarily to scale. Off there. Okay, so x less than 7. So less than, strictly less than, that's a parenthesis, and we're going to the left. So there's our first graph. Second one, x is less than negative 6. So we got here, and less than. All right, so no graphs here, only one graph here. 2 graphs starts here. So our combined graph is going to start at negative 6 and go all the way to the left. And in interval form, that is negative infinity to negative 6. All right, last situation, we're going to look at graphs that are pointing in opposite directions, but no overlap. So we got x less than -7. So graph that one. Strictly less than, so parenthesis. Second graph. X is greater than or equal to -8. So greater than or equal to means the bracket. And we're going to the right. So now we have two graphs pointing in opposite directions with no overlap. So now the intersection is all the places where we have two graphs. Well, here we only have one, here we have 0, and here we have 1. So there's no place on the entire graph where there's any overlap. There's no number that's both less than -7 and greater than 8. So that means we don't graph anything. The graph is empty. And the solution set, since there are no elements in it, that's the empty set. Now we're going to do unions of intervals. So as we saw, unions are any number that is in either one of the sets. It doesn't have to be in both. So that's going to affect the way we graph and find the solution set in interval form. So let's take a look at case 1. So in this case, we're going to look at two graphs pointing in opposite directions with no overlap. Now when we do unions, the key word is or. So that's how you can tell whether or not we're doing union or intersection from the compound inequality. It's all from that keyword, either and or. And's intersection, or is union. Now let's graph these. X less than 7. Move this over, 0, 7, and 11. Okay, x less than 7. So it's strictly less than, so that will be parenthesis and all the way to the left. X is greater than or equal to 11, so we got a bracket there, and all the way to the right. Alright, now with these we don't need the overlap. To combine, oops, I really shouldn't have put those both on the same graph. A little mistake there. Let's get rid of that. Okay, so second graph, bracket all the way to the right. All right, now we're going to graph on the final graph here anything that is in both of these. So here we've got one graph. So that's all we need. So that's going to be included in the set. So we'll graph this part. Now here we've got none. No graphs anywhere here. So this is going to remain unshaded. Over here, we've got this graph. One is enough, so we'll shade this part as well. So there's the combined graph of x less than 7 or x greater than 11. X greater than or equal to 11. So you have two parts of this graph. So that'll happen when you have an or and the graphs are pointed in opposite directions with some space in between. And then if we want to write this in interval form, we're going to have two parts to the interval form as well. We're going to have one part for this piece and one part for this piece. So this piece is -infinity to 7, parentheses. And then this piece over here, start with a bracket, 11 to infinity. So there's the two parts of the graph. And what are we doing? We're creating a union. So we'll put the union symbol in between them. And that just means both of these are included in the solution. So there's interval form. So get used to writing sets like that with two pieces with a union in between them. Your turn, number 5. First graph, x is less than or equal to -2. So bracket for less than or equal to, and all the way to the left. X is greater than 3, so a parenthesis for greater than, strictly greater than, and all the way to the right. Oh darn, I did it again. There we go. Okay, so there's our two graphs. All right, now we're going to go down and see where we have at least one. So here we've got one, so this will be in the solution. And here we have none, nothing here. Here we've got one, so we'll include this in the solution. All right, so there's our final graph for x less than or equal to -2 or x greater than 3. And in interval form, all right, we'll do this piece first. -infinity to -2. And over here, we've got 3 to infinity. And then we'll combine it with a union. All right, next up, we're going to look at an example of pointing in the same direction. So union case 2, we're going to do x greater than 0 or x is greater than 3. So first graph, x greater than 0, strictly greater than is a parenthesis all the way to the right. Greater than 3, parenthesis all the way to the right. All right, now we want anywhere where there's at least one graph. So we have 0 graphs here. Here we have 1. So we include that one. And now this one, there's no point in adding anything else to the graph because that part is already covered. So there's our graph. Actually, as it turns out, it's exactly the same as the larger graph. And then in interval form, we're going from 0 to infinity. So there's the union of x greater than 0 or x greater than 3. Your turn, number 6. So less than or equal to 5, less than or equal to is the bracket, and all the way to the left. X is less than 3, as a parenthesis, all the way to the left. Right, over here we have no graphs, so we're not going to shade this part. Over here we have 1, that's enough for a union. So bracket and shade all the way to the left. And then this part is already covered, so we don't need to add any more, and there's the graph. And so this will be negative infinity to 5 with a bracket. Case 3. We got x greater than -1 or x less than 4. X greater than -1. All right, so parenthesis here all the way to the right. X less than 4, so you got a parenthesis all the way to the left. All right, now we want to graph anywhere that has at least one graph. Well, here we have one graph, we got this one. So we're going to shade this part. And here we have 2 graphs, so we'll definitely want to include that part. We go all the way out to here, and here we have a graph as well. So that means we're shading everything. Every number is a possible solution to this, because any number we pick is either going to be greater than -1 or less than 4. Works with anything. So how do we write that? Well, the answer then is all real numbers. Write that from negative infinity to positive infinity. All numbers work. All right, last page, you got some mixed practice. Please go through those at your own pace. Pause the video, work through those, and compare them with what I get. So having mixed practice is really valuable because you have to, instead of being told what type you're working on, you're going to have to be able to identify the type. And that's what you're going to need to be able to do on the homework and the exams. So do that first, identify the type, and then go through the procedure. And with these, you actually have to solve the inequality first. So a little bit more with these. Part A. We've got an and, so that is an intersection. We're going to solve these. So when we solve the first one, we get x is greater than or equal to -4. So graph this one, starting here, go all the way to the right. Here we got x greater than or equal to -3. All right, so there's the second graph. Now we're looking for the intersection. For the intersection, we need both graphs to be present. No graphs here, so we don't include that. Only one graph here, so we do not include that. But here we've got both graphs. So we'll start here at -3, bracket, and go all the way to the right. So then in interval form, -3 to infinity. So we'll solve these. So x greater than 3, or x less than 1. So x greater than 3, strictly greater than, so we got a parenthesis there. X less than 1, got a parenthesis there. And now we're looking for, see, we have or. Or is union. So union means only one of them needs to be there to be in the solution. So we've got one graph here, so that's in the solution. We've got no graphs here, so that's left out. And over here, got that graph. All right, so we got two pieces here to our final solution. And then in interval form, we'll do these two pieces and union them together. So we got -infinity to 1, union 3 to infinity. C. Oh, we'll solve these inequalities. So we have x less than or equal to 5, or x less than or equal to 2. So less than or equal to 5, we got a bracket here, go to the left. X less than or equal to 2, got a bracket here, going to the left. Now, or, this is union, so that means it can be in either one of these. All right, we have no graphs here, so we're not going to include this. We have one graph here, so that's good. And this graph is already here, so we're all set there. And interval form, we got -infinity to 5 with a bracket. Part D, we're going to solve these. Get x less than -2 and x greater than -8. So x less than -2 is strictly less than, so that's the parenthesis going all the way to the left. X greater than -8. What in the world? Pardon me for 1 second here. There's -2. That's better. Okay, greater than -8. So now we're going this way. All right, so now we want and, that's the intersection. So that's where we have two graphs. Here we only have one, so we won't include that. In the middle here, that's where we have two. So we'll graph this part. Here we only have one, so that's not included. So there's our solution between -8 and -2, and in interval form, -8 to -2. E. And we already solved these. Oh, no, we didn't. Oh, they were slightly different in part C. I'll go ahead and solve them. So we got x less than or equal to 5. Or x greater than or equal to 2. Okay, less than or equal to 5. So we got the bracket there all the way to the left. Greater than or equal to 2. And now we're doing the union. We have an or. So it could be in either one. Anywhere we have at least one graph, we're good. So we have one here, we have two here, and we have one here. So the whole number line is covered. So our solution set is -infinity to +infinity. F. So solving these inequalities, we get x greater than 1 and x less than -2. All right, greater than 1 takes us to the right with a parenthesis, which is strictly greater than. Second one, we're over here at -2, going to the left. And now we have an and, so we have an intersection. We want the places where we have two graphs. We have one here, 0 here, and 1 here. So the graph is empty. And the solution set is the empty set. So when you work on these, make sure you practice identifying the type and then going through the procedure. Have a great day, everyone.